school, I think most people will have an intuitive notion of what continuity means, right? Because there's an English meaning associated to it. The word continuous is used in English in our regular day-to-day language. And because of this, we all have an intuitive sense of what continuity is. So what I want to discuss today is how faithful is the mathematical notion of continuity to these intuitions. The intuition that comes from day-to-day English usage, the intuition that we all have from school, and the intuition that we have refined even after a course in proper analysis. So these are the kind of topics that I would like to discuss in today's session. So first, maybe I would like to hear from somebody. How would you introduce, or how would you introduce the concept of continuity to maybe somebody new to it, new to the topic? If somebody has some ideas to share, I would be glad to listen to it.
Something which doesn't break.
Something that doesn't break. Okay, so something that's a very good thing. So opposite of continuous is something that has breaks in it, right? So we have been attending classes for 2 hours. In your case, that's what is happening, right? Continuously, you have attending lectures for 2 hours. No, it was not continuous. There was a 5-minute break in between. So the opposite of continuous is something which has breaks in it. Right? That's a very nice intuition. Thanks. So that's maybe the starting point of what continuity means. Something that does not have breaks or gaps in between, that is called continuous. Very nice. So this in fact was the first intuitive notion with which, say, Newton or Leibniz worked with continuity. They did use this idea of continuity as some function which does not have breaks in it. Any other intuition that you have? Like somebody else would like to add something about it?
You can control the output by controlling the inputs.
Okay, the output and input are somehow related. You can, but you can always get the output from the input, right? Isn't that the definition?
No. I mean, you can control the
error.
Control.
Okay. Control.
Yeah.
Okay. Okay. Nice. You can control the output by controlling the input. Yes, this is actually the modern version of continuity. Yes, that's very good. Like if the inputs are close enough to each other, then the outputs are also close enough to each other. That's the modern notion of continuity in some sense. And it's actually very different. So this is something that is very interesting, right? Now there are 2 different notions, or at least seemingly 2 different notions. One is continuous is something that does not have breaks in between. Second is if inputs are close, then outputs are also close to each other. These are 2 different notions of continuity. Are these 2 notions same, or are these 2 notions different? What do you think? I think Chetana gave one definition and Shubhajit gave the other definition. So are these 2 definitions same, or are they different?
They are same. They are same.
They're same? Okay. Okay. What do others think? Are they same? How many of you think that they are same?
Yes, they are same.
Okay.
Yes, same.
Second definition is related to stability.
Okay. Okay. Second definition is related to stability. Okay. So a lot of people are saying that these 2 definitions are same. Okay. So the 2 definitions are same is what many people are saying. Let's try to explore this. Okay. Let's try to explore if these 2 definitions are same or different. To understand whether these 2 definitions are same or different, first of all, we have to make it precise, right? This in fact is what I want to talk to you today. In fact, this is exactly what I wanted to talk about. There are 2 intuitive ideas about continuity, precisely the two definitions that came up in our class, right? The 2 definitions are of something that does not have breaks in it. And the second thing is, by controlling the input, you can control the output. In other words, if the inputs are close enough, then the outputs also should be close enough. These are the 2 different definitions that we have. Now we want to make this precise. Okay, so to make this precise, I am going to start writing, because without writing, some of this will become very difficult. So let me start sharing my screen, and we will go through it step by step. Okay, so let's write these things down. There are two definitions that we came up with. Let's call these definitions D1 and D2. What is the definition D1? D1 says that continuous means no breaks. D2 says that if inputs are close enough, then outputs are close enough.
For D1, we can say it's not perfect one.
Sorry, can you repeat what you said?
The D1 definition, no breaks, we cannot say it's a continuous definition, because if I take 1 by x, as x tends to 0, the limit does not exist. So even though the graph of 1 by x has no break, if you look at from 0 to infinity.
Actually, you do have a break here, right? So for example, to call this a graph, if suppose you are looking at, it depends on how you look at this graph. Okay, my drawings are really bad. Let me draw it, rub it and draw it again. That's a good example. Let's discuss this example. So suppose we are looking at the graph of 1 by x, right? If suppose we are looking at the graph of 1 by x, in which interval are we looking at this? That is very important. Do you mean the open interval, open 0 to infinity, or close 0 to infinity? Which interval are you talking about?
I'm talking about closed interval 0 to infinity.
Closed interval 0 to infinity. If suppose you are looking at this function, f of x is equal to 1 by x, then this function is not like as it is not defined, it is not, we cannot evaluate this function at 0. 1 by x makes sense only when x is not equal to 0. If x is equal to 0, then f of x is equal to 1 by x does not make sense.
But there is no break. If you can identify, if you look at the graph, we don't have any, we cannot able to find a break here.
No, that's the whole point I'm trying to focus on. As of now, we have not defined the function at 0.
Okay.
We have to define the function at x is equal to 0, right?
Yes.
If suppose we define the function at x is equal to 0, then immediately we have a break. For example, how do you want me to define the function at x equal to 0?
If we have taken a, there is not exist or infinite, we can take.
No, infinity is not a number, right?
So we can define function at 0 to be 0. Let's say at when x is 0, f of x be 0.
Great. So let's define at 0, let's define the function to be 0. Now notice that there is a break in the function.
In that
right?
case,
Now there is a break in the graph, because at 0, the function is defined to be equal to 0. Maybe using a different color will help you see it. Okay, maybe I should use red color. So notice that at 0, the function is here, and after 0, it is here. After 0,
yes, sir, there is a break.
So there is a break actually.
yes.
So if you define the function on closed interval 0 to closed 0 to open infinity, if the function is defined from closed 0 to open infinity, then the function has a break.
Okay.
And that is precisely why it's not continuous on this domain.
Yes.
But on the other hand, you have a point. If you are restricting your function to open 0 to infinity, okay, then this function is indeed continuous.
Yes.
And that is why the graph of the function does not have breaks in it.
Yes. Yes.
Right? So this is exactly, so you are making a good point. So, but there is another reason why this is not a good definition. This is not a good definition because the word breaks is not so clear to us. How do you make it precise is the kind of question that we need to ask. Okay, so what is the meaning of break? Okay, intuitively we see what break is. We can understand, we can geometrically, if I draw a picture, you will understand whether it has a break or not. But otherwise, how do I define a break?
If you are able to move one point to another point without having any disturbance.
Okay, that's the question, right? Then I will ask you a question. Let's now look at another example of a function. Suppose you look at this function, f of x is equal to, x if x is irrational and 0 if x is rational. Is this function continuous at 0? What is your...
Yes.
Yes, continuous at 0.
Continuous at 0 actually.
Does it have breaks?
Many.
Even near 0, even if you are focusing very near 0, on a slight, like a very small neighborhood of 0 also, if you notice, there are a lot of
breaks.
this function.
Yes.
There are several breaks, right?
Yes.
How much ever small a neighborhood of 0 you consider, there are still a lot of breaks. Whatever breaks means, you cannot go from one point to another without breaks.
Yes. That's why we have a disturbance there between, if I want to move from any point nearer to 0 to that 0 point, I cannot able to move smoothly. We have, because of they have disturbances.
Now a new word has come, smoothly. Okay, smooth now in mathematics sometimes has a different meaning.
Yes.
So again,
that smoothness is something different actually.
Let's keep it there, because that is sometimes useful, because our intuition about, in fact, if I ask you to draw a continuous image, mostly what you will draw will be a differentiable function also. Maybe at best somebody might draw
mod x function.
Something like that looks like this, but that's the worst people draw. The worst people draw is something that looks like this, right? Which has some spikes in it.
Yes.
Which is also like not so far away from being smooth. Okay, it's not really smooth. There are few points where smoothness is broken, but only at few points smoothness is broken. Everywhere else the function is smooth. So our intuition is drawn, like a lot of our intuition is drawn from these kind of examples that we draw. Okay. Yes. That is perhaps part of the reason why, and these intuitions are being used when we are intuitively trying to understand no breaks, right? Because that is what I am trying to say. This no breaks in some sense is not precise.
Yes.
That is what I really want to stress upon. If you believe that it is precise, I encourage you to think about it. And in the next class, if you believe that, no, I can make it precise, then come up with a precise definition and let me know. But I believe that this cannot be made precise. This idea of no breaks is not really something that we can make precise. Okay? But there is something very close to it that can be made precise. So I'm going to explain what that is, which is not exactly equal to this, but it captures our intuition to a large extent. Okay, so there is some property that is very close to no breaks. So let us see what that property is. That's the next thing that I want to discuss. So now let us look at some function. Let us say there are 2 points A and B. And for these 2 different points, there are some values. Let us say f of A and f of B. Notice that here I have drawn f of A to be bigger than f of B. It could have been the other way also. Okay, it's just, but it's either this or that. So I just drew one of the pictures. That's all. So suppose I have these. Okay, then in the graph I can plot those points. I can plot the points A comma f of, oh sorry, that's the wrong point. I can plot the points A comma f of A and B comma f of B. Now suppose the graph of this function that is between A and B is continuous. That means it does not have any breaks. Then I would expect that if I draw a line somewhere in between, okay, a line with y coordinate, line such that the y coordinate lies between f of A and f of B, then I would expect that this curve has to intersect it. However you draw this graph, you know that it has to intersect somewhere. You intuitively feel that. Okay, whatever I have drawn is actually a very bad picture. That's not a function. But even if I have something like this, notice that it intersects somewhere. It has to intersect this red line somewhere. This is something that we intuitively feel, right? If I have to draw this without, if I have to draw it continuously, if there are no breaks, if there is something connecting f of a comma f of a and b comma f of b, then it has to intersect this red line somewhere or the other. That is something we intuitively feel, right? Does that make sense?
Yes, sir.
Yeah. So this property, maybe you have already heard of this property. This property is called as the intermediate value property. Right? What does this mean? Intermediate value property means that if you have an interval a, if you take 2 points a and b, if you have an interval, if you have the function is defined on an interval a comma b, and if f of a has some value and f of if at a it has a value f of a and at b it has a value f of b, then the function has to take some value, like at some point between a and b, the function has to take okay, sorry, I have to say it again. If you take a value between f of a and f of b, then the function has to take that value at some point between a and b. Let me repeat. If at a you have the value f of a and at b you have the value f of b, and c is some value between f of a and f of b, then there is some point between a and b where this value c is attained. This property is called the intermediate value property, and I'm sure you have all seen that.
Sir, this will be hold whenever f is continuous. Otherwise, it is not possible.
So again, let's try to understand these things clearly. So that, however, is not true. So it's not true that only continuous functions satisfy intermediate value property. That's what we are ready to come up with. That's the whole point. So you have raised an interesting thing. So the idea, so what we have seen so far is, if suppose a function does not have any breaks, then we should expect that it should satisfy the intermediate value property. So we can redefine D1 as intermediate value property. Okay, we can redefine D1 as a function that satisfies intermediate value property. Now the question is, now because I already said that somebody said this, let's try to see it. So the claim was that only continuous functions satisfy intermediate value property. Is this claim true? I claim this claim is not true. I claim there are functions that are not continuous, but intermediate value property is satisfied.
Yes, sir.
Can somebody give an example?
Sir, step function.
I am saying that it is not whole, even though intermediate property satisfies, it is not continuous.
No, I didn't understand.
No, it is not necessary.
I am saying that even though if the claim, whatever we are saying that there exists a C, that property may satisfy even though it's not continuous. That's what I'm saying.
Okay, can you give an example then? If you're making that claim, can you give an example? Can you give an example of a function that satisfies intermediate value property, but it is not continuous?
Sir, step function.
Step function.
Not all step functions, sir. We can take a piecewise function.
Okay, let's
Yes,
look
there are many
step by
examples.
step. Let's go step by step. Let's go step by step. Suppose I take a step function. Okay, this is a step function. Do you agree? I'm going to write this function precisely.
But it's not satisfies.
-1 if x is less than 0 and 1 if x is greater than or equal to 0. This is a step function. Does this satisfy intermediate value property?
Yes, sir.
No.
No, right? It doesn't satisfy intermediate value property. Why? Because notice this. Notice that at this point, if you take this point, the value of the f of x is -1. Okay? If you take this point, f of x is equal to +1. If you take a point between -1 and +1, this graph is not intersecting that line at all. There is no point between these 2 points. There are no points between these 2 points where the function takes this value. See, so this function does not satisfy the intermediate value property.
Yes.
Right? So step functions does not satisfy. In fact, no step function will satisfy intermediate value property.
Yes, but we can have a piecewise function which satisfies.
Can you give an example?
F of x equal to x.
Okay,
For
great.
x less than or equal to 1.
F of x is equal to x.
For x less than or equal to 1.
X less than or equal to 1.
And minus 3 by 2x plus 4.
Minus 3 by 2x plus 4.
For x greater than 1.
For x greater than
1.
Let's try to see the graph of this. So this function, let's try to draw the graph of this function. So this is 1. At 1, it is equal to, after 1, it's going to x less than or equal to 1. So, so what is happening is till x is less than
x less than or equal to 0, sir. Please take x less than or equal to 0.
Okay. So here it's 0 and here it's greater than 0, right?
Yes.
Okay. So till 0, it's x. And after 0, it is 3 by 2x plus 4. Okay. So it starts from 4. And then it is going 3 by 2x. So it goes something like this.
Down. No, so it's
minus. Oh, sorry. You have written minus.
Yes, it should go down.
Like this. Very good. Right? Does this satisfy intermediate value property?
Yes, obviously, sir.
It does not satisfy intermediate value property, unfortunately. Let us see why. Okay. Let us see why this does not satisfy intermediate value property.
Yes.
Suppose these are my 2 points. Let's say take this point A and take this point B.
Okay.
Okay. What is the value at B? Okay. At B, the value of the function is here. And at A, the value of the function is here.
Okay.
Right. Now take the value, no, take this value. This certainly lies between f of A and f of B.
Yes.
But notice that there is no value between A and B where this value is attained.
Yes, yes.
So this does not satisfy the intermediate value property.
Yes, yes, correct.
Correct? So this function does not satisfy the intermediate value property. Okay, so there is another example that somebody is trying to give. If x is less than 1, you take it to be x. And if x is greater than or equal to 1, you take x minus 1. That function also will not satisfy the intermediate value property for same reasons. You have to take A and B small enough, and then you can see that it will not satisfy intermediate value property. In fact, this is something.
The example is sine 1 by x.
Ah, nice. Now you have come to the point. Amazing.
And around 0, around both sides of 0, and you define at 0 anything like sine 0. Amazing. So in fact, let me just say this. In fact, this is something I want you to try. This is interesting. So if suppose, see, there are 3 kinds of discontinuities. Maybe we have all seen that, right? There are jump discontinuities. There are removable discontinuities, and then there are really ugly discontinuities, right? Ugly discontinuities are of a broad category. Within that, there is so much hidden. But if suppose our discontinuity is jump discontinuity, then it cannot satisfy intermediate value property. Any function with a jump discontinuity will not satisfy intermediate value property. And that is why intermediate value property looks like the correct notion of continuity to us intuitively. If a function has a jump discontinuity, then that function cannot satisfy intermediate value property. I want you to think about it. Okay? What I'm like, are you getting what I'm trying to say?
Yes, sir.
Right? If there is a jump discontinuity, then you should not expect the function to be then the function will not satisfy intermediate value property. But on the other hand, there is another example that somebody had told. I started losing track of who is telling what. But still, there is another example of a function f of x is equal to sine 1 by x if x is equal to 0. If x not equal to 0, And you can take any value, like let's say any value between -1 and 1, you can take. Let's just take 0 for simplicity, if x is equal to 0. This function, okay, let me try to draw the graph of this function. The graph of this function is very difficult to draw, but let me still try to draw it. So the graph becomes, the frequency increases as I come closer and closer to 0. It's all at 1. The height is same. I am not drawn properly, but that's supposed to be how it is. The frequency just increases as I come closer and closer. So it looks something like this, right? Why does this function satisfy the intermediate value property? Can somebody explain why this function satisfies? Maybe preferably somebody who is like in the sense, whatever, like why does this function satisfy the intermediate value property?
The sign assumes all values between -1 and 1.
Sign assumes all values between -1 and 1. That's correct.
So for any number between -1 and 1, we have a pre-image. We can find that.
That is true, but there is something more specific we have to do, right? So that is the difference. That is partly why there was this confusion. It is not whether, so this function assumes every value somewhere or the other, but the issue was that it does not assume those values in this neighborhood, in this interval. That was the issue. So this value is attained here. Okay, this value is attained here, but the problem was that it is not attained in this interval. Between A and B, it was not assumed. That was the issue. Right?
Jump discontinuity maybe? Jump discontinuity?
No. I'm saying that to satisfy intermediate value property, it is not enough that this value is attained somewhere. That value has to be attained between A and B. So there is something more that you have to do here. It's not enough to say that every value is attained. Given any 2 points A and B, and any value C between f of A and f of B, there is some value between A and B where this value C is attained. Right? Let's write it down. Given A comma B in R, and C lying between f of A and f of B, okay, or C lying between f of B and f of A, okay, one of these two, there exists a D in the interval AB. It has to be in the interval AB, otherwise it's not intermediate value property, it is something else. Okay, there exists some D in the interval A to B such that f of D is equal to C. That's what we want. We are claiming. We are claiming something stronger. So it's not enough that sign takes all values. We are doing something stronger. Right? Are you getting what I'm trying to say? Because that was exactly the confusion that was happening here. Am I making sense?
Yes, sir.
Yes.
Right? So that is the important point. So we have to take, so suppose I'm taking 2 points, right? So there are 3 possibilities. Either both those points lie to the same side of the x-axis, same side of 0, because they can both lie to the left or they can both lie to the right. If they both lie to the same side, say left for instance, then clearly the function is continuous and everything, and we can easily see that the intermediate value property is satisfied here, right? Any value between this is attained. That is easy to see. Similarly, if both values are towards the right also, the same thing is satisfied. The same thing. It's easy to see that all values are, any value in between will be attained. The really complicated or confusing aspect is when one point is to the left and another point is to the right. Whenever this happens, irrespective of what A and B, every value between -1 and 1 is attained in between A and B. Therefore, intermediate value property is satisfied for this choice of A and B also. Am I making sense?
Yes, sir.
Right?
Yes.
If you take A and B to be on both sides of 0, irrespective, even if A is minus 10, like minus 1 by 10,000 and B is 1 by 10,000, still in between these two values, F takes all possible values between -1 and 1. So clearly it is, it satisfies the intermediate value property.
So the function starts oscillating in the neighborhood of 0. That is the
Exactly. So it's oscillating everywhere, but it's oscillating very rapidly near 0. It's oscillating so rapidly near 0 that no matter how small an interval you take around containing 0, in that small interval, all values are taken. That's not true if you take some other interval. For instance, if you take this interval, then all values are not taken. Only values from here to here are taken. Right? If you take this interval, then only values from here to here are taken. All values between -1 and 1 are not taken. But still, intermediate value property is being satisfied here. Why? Because if you take any value between these two values, there exists an x where that value is attained. So still, intermediate value property is satisfied. Correct?
Yes. Yes, sir.
Yes, sir.
So that's the idea. So this is a function which, so again, so let's come back to it. We said that this function is in some sense like the intermediate, like D1. Having no breaks is like D1. That was our point. Having no breaks was like D1, and D2 is precisely the rigorous definition that we have all seen using epsilon and delta. The rigorous definition using epsilon and delta that we have defined, that actually is, this is just the intuitive formulation of that rigorous definition using epsilon and delta. So what we are seeing is that this function, however, sine 1 by x is not continuous with respect to definition 2, but it is continuous with respect to definition 1. So what this means is that the two definitions are not one and the same.
D1 is necessary condition.
D1 is necessary. Okay, D1 is necessary. It's not sufficient in some sense. But okay, now I have a question. But why did we, okay, so we can see that the two definitions are not one and the same. Okay, a function can satisfy D1 and not satisfy D2. Okay, so what did we see here? A function can satisfy D1 but not satisfy D2. Can the opposite happen? Can a function satisfy definition 2 but not satisfy definition 1? That also can happen.
That can happen only on disconnected domains.
I think, sir, the definition D2 is more powerful because that leads to the uniform continuity.
Okay, now there are so many interesting ideas coming. Thanks a lot. So there is, I'm going to take it one by one. Okay. First of all, somebody talked about disconnected domains. This is exactly the kind of thing I wanted to talk about. Thanks for bringing it up. So let's say disconnected domains. Okay, let's talk about what happens when we have disconnected domains. Let's look at an example. The simplest example of a disconnected domain is something that looks like this. This is a disconnected domain, right? Now let us look at a function from this to R. How am I defining this function? I am going to define this function as f of x is equal to 5. Okay, how does the graph of this function look? The graph of this function looks like 0, 1, 2, 3. The graph of the function looks like this and this. Now notice that for this function, D2 is satisfied. Okay, D2 is true, but D1 is not true. Right? there is a break. In the graph of this, there is a break. Right? I have to draw here and then lift the pen and draw here. So D1 is not true. But D2 is true. If the values are close enough, if the input is close enough, the outputs are close enough. In fact, the output is equal, irrespective of what the input are. Right? The output does not change with input. It's always the same input I am giving. So this satisfies D2, but D1 it does not satisfy D1.
It's locally continuous.
It's actually continuous everywhere. Like according to D2, it is continuous. That's why continuous meaning what is the question. So according to D2, this is continuous. This satisfies D2, but it does not satisfy D1. And the rigorous definition that we use using the epsilon and delta is actually a rigorous formulation of D2, not D1. Okay. Am I making sense? Of course, we can give more complicated examples also, right? Like for example, a complicated example would be a function f from say Q to R, defined as f of x is equal to x. This function is continuous according to definition D2. If the input is close enough, the output is close enough. In fact, the difference between the inputs is equal to the difference between the outputs. So if inputs are close enough, outputs are also close enough. However, notice one thing. Notice that 0 less than root 2 less than 0 less than root 2 less than 2. Okay, 0 is less than root 2 is less than 2 because root 2 is 1.414. Okay, or let me just take it 1 less than root 2 less than 2 because root 2 is 1.414, and f of 1 is equal to 1, f of 2 is equal to 2, but there exists no x such that f of x is equal to root 2. So this does not satisfy the intermediate value property. So there's a break in some sense. There's a break in some sense, but this satisfies definition 2. So this satisfies definition 2, but does not satisfy definition 1. And this is exactly what somebody had brought up. This happens precisely when, like, if suppose a function is continuous with respect to D2, then it will not satisfy D1 only if the domain, or at least the place where the function is continuous, is disconnected. Here something similar is happening in this function also. Where is that function that I wanted to talk about? Yeah, this function. Here also there is some issue, right? Here also there is lot of breaks. Why is there a lot of breaks? It's not because the function is defined only on a disconnected domain. The function is defined on a connected domain, but the function is continuous only on a disconnected set. In fact, it is discontinuous only at 0. And 0 is like, that's the issue. So it's like, it's a kind of not a nice set where the function is continuous. So that is part of the reason why there is a problem here. Right? So these are the kind of things. So D2 does not imply D1. D1 does not imply D2. Right? What did we see now? In using all these examples, we saw that D1 does not imply D2 and D2 does not imply D1. But we thought that this is implied. In fact, when we started with, people were telling that D1 and D2 are one and the same. Almost everybody said that D1 and D2 are one and the same. But as we can see, D1 and D2 are not one and the same. Now there is a question. Okay, if suppose D1 and D2 are not one and the same, why do you prefer one definition? So nowadays most of us use D2 as the correct definition, not D1. Why do we choose D2 as the correct definition and not D1? That's the next question that I'm interested in. Is it clear to everyone that D1 and D2 are different?
Yes, sir.
Right? So D1 and D2 are very different from each other. The next question is, suppose there are D1 and D2, there are two definitions, there are two different definitions for continuity. Why do we prefer one definition over the other? Right? Because in fact, the word continuous is more related to D1 and not D2. D2 sounds, okay, it's fine, but how did you come up with this? It did not, I couldn't think of this when I heard the word continuous. Continuous is more related to not having breaks. So why did I choose D2 and not D1? Of course, they are like D1 does not imply D2, D2 does not imply D1. So why should one definition get priority over the other definition? That's the question that we are interested in. Do you like? Have you thought about this? Like this idea that why do we pick one definition over the other? That's the kind of question I am asking. How do we choose definitions? Is it getting crazy?
Maybe which one has more examples or more applications?
Very good, very good. So that's the whole point, right? Like, so there are 2-3 criteria by which we choose what definition to choose from. First of all, intuitively we feel if suppose a particular function is continuous with respect to one definition, does it match our intuition? If a particular function is not continuous with respect to our definition, does it match our intuition? Now, these questions we should answer. Now, we already saw that both definitions have some issues. Like, for example, this function is continuous at 0 is kind of unintuitive. But definition 2 implies that this function is continuous. So there is D2 also has this issue that it does not satisfy our intuition always. But D1 also has an issue. Intuitively, we don't feel that sine 1 by x should be continuous. But D1 will imply that sine 1 by x is this function is continuous. So they both exclude some functions, or they both tell some functions that we think should not be continuous as continuous. So if our aim is to see whether it matches intuition, both D1 and D2 fails. Okay, that's the first lesson. Both D1 and D2, they give rise to examples of functions that should not actually be continuous according to our intuition, but they are continuous according to this definition. Both definitions have this flaw. So that is not how we determine. It is not looking at, we did not determine which definition to take based on examples. We used something else. What is this something else? That is related to the point that somebody had brought up. It is based on what kind of properties do these continuous functions have. In other words, if suppose a function satisfies D2, what properties will that function satisfy? If a function is satisfies definition 1, what properties do they have? And so on. This is the interesting thing. So it turns out that D1 functions satisfying D1 do not satisfy good properties. What are these good properties that are not satisfied? Okay, let's try to see it. I will first write those properties and then we can discuss like examples that fail this. Okay, the first property that function satisfying D1 fails is f satisfies intermediate value property does not imply that f is bounded. This is one issue for using definition 1. Second problem is f and g satisfies IMP, intermediate value, sorry, IVP, I don't know why I read IMP, intermediate value property does not imply f plus g satisfies IVP. Okay. These are things we want for continuous functions. Continuous functions are bounded. Continuous functions on at least closed intervals are bounded. So here even on closed intervals, this is not necessary. Right? Continuous functions on closed intervals need not be bound, should be bounded. It's one of the properties we require. It's used in so many proofs. Continuous functions on closed intervals are bounded. That property will not be satisfied if you use definition 1. And that property, the continuous functions are bounded on closed intervals, is used in many theorems. And that is related with uniform continuity and things like that. Somebody had brought that point also. Another property we want is that if f is continuous and g is continuous, we want f plus g to be continuous. That also is violated here. Even though f and g both satisfy intermediate value property, it does not mean that f plus g satisfies intermediate value property. Can you come up with examples for these? Is the next question. Can you think of examples? Can you think of some examples? Okay, I will give you a clue. It has something to do with sine 1 by x.
The examples for 1 and 2. I was asking for examples of 1 and 2.
Yeah, examples for 1 and 2. And I can give a hint. It somehow uses sine 1 by x.
Fx is equal to 1 by x on open 0, infinity for the first one.
Sorry. Can you say f of x equal to
Fx is 1 by x on 0, infinity.
1 by x on 0 to infinity.
Open 0, infinity.
See, that's what. So I should have f satisfies IVP. Okay, let's say it. F defined on a closed and bounded interval. F defined on closed bounded interval satisfies IVP does not imply that f is bounded. This is not defined on a closed bounded interval. That's the problem. I want it to be defined on a closed bounded interval. Even if it's defined on a closed bounded interval and it still satisfies IVP, you can still not conclude that the function is bounded. That's the important thing. Because as I said, what we are interested in is the theorem that, of course, we know that continuous functions need not be bounded. 1 by x is an example. 1 by x on 0 to 1 itself is an example. Or f of x equal to x is not bounded, right? If suppose these conditions are not satisfied, then f of x equal to x is continuous, but it's not bounded. So that is a trivial example. That's not an interesting example, right? F of x equal to x is not bounded. But f of x equal to x is bounded on every closed bounded interval. So we are looking at closed bounded intervals. Otherwise, this statement is not so interesting.
F of x is equal to 1 by x on minus 1, 1, except 0.
1 by x
on minus 1, closed interval minus 1, 1, except 0.
X not equal to 0. Okay, we are looking at f from minus 1 to r.
And at 0, we define it to be 0.
This function does not satisfy the intermediate value property. Okay, this
one will be 0 to pi tan x, and at pi by 2 define it to be 0.
Sorry, can you say it again?
Yeah, from 0 to pi.
F of x is equal to, okay, first I will write it. F is from
0 to pi
to r.
If it's, yeah.
And f of x is equal to
tan x when x is not pi by 2.
X is not equal to pi by 2.
And 0 at pi by 2.
0 at pi by 2. this also does not satisfy IVP.
Oh, I guess it will be minus 10x for the for one side and plus 10x on the other side.
No, whatever you do, this will not work. Okay, these things does not satisfy IVP, unfortunately. So maybe that is something that you should try to spend some time on. What functions satisfy IVP? That requires some thought. Okay, so these are not functions that work very well. Like, it's easy to see if you know the picture of the tannets. From that, it
Yeah.
not satisfying.
So we can do this way, sir. We can have 1 by x and on either sides of 0, and we can merge that, let's say, to 0 at 1 and minus 1. So the actual form will be a little difficult. So what I'm trying to say is, from f at minus 1 is 0, it goes to minus infinity from on the left side of 0. It goes to plus infinity on the right side of 0, and it goes to 1 0 at x equal to 1.
Can I write it? So can you say it all again? So
yeah, if x is equal, if is defined from minus 1 to 1. So if minus 1 is 0.
At minus 1, it is equal to 0. Okay.
Yeah.
0 if x is equal to minus 1.
0 if x equal to plus 1.
0 if x is equal to plus 1.
And if x tends to minus infinity for when x is tending to 0 from left.
X tends to 0 from left.
From left. And tends to plus infinity when x tends to 0 from right.
This is minus infinity, okay? This is
yeah.
Okay.
Yeah, it will be like f of x is equal to the same, like 1 by x minus 1 for x greater than 0.
See,
1 minus x
of this.
Yeah.
1 minus x by x.
You're looking at a function.
No. The left side will be the downside, down way.
Oh, okay. You want you want it goes to minus infinity. Okay. So like this and like this. This again does not satisfy IVP. Why? Because let's try to see it, right? So let's take these values. Let's take these two values. Okay. So at this value, I get this point. So at this point, I get this value. At this point, I get this value. So if I take a value between these two, okay, if I take a value between these two, say, let's say this value is not attained in this interval.
Okay.
It again does not satisfy IVP.
Oh, 1 by x sine 1 by x. Okay, sorry, yeah.
Okay.
Yes.
Now finally there's a correct example. So f of x equal to 1 by x sine 1 by x if x is not equal to 0, and 0 if x is equal to 0. This function satisfies the intermediate value property. It's not easy to see, but it satisfies the intermediate value property. So it requires.
How to imagine the graph of this function?
Okay. So, okay, maybe you have all seen the graph of sine 1 by x, right? So let's try to start from that. In fact, this is the basic idea between a lot of things. So the graph of sine 1 by x looks something like this. The frequency increases as I go closer to 0, right? That's the whole point. But now, not just that the frequency increases, as I come closer and closer to 0, the value becomes greater and greater. So it's not just that the frequency increases, the altitude also increases. As I'm coming closer to 0, it's not just the frequency that's increasing, the altitude also increases. Okay,
it gets scaled along the graph of 1 by x.
Let me do one thing.
Sine 1 by x gets scaled along the graph of 1 by x.
Exactly. So let me stop sharing and let me share something else, because I can share using, so just 1 minute. Let me just do something. Again, for all these things, the good idea is you can use software, right? So let me just take, I don't know whether how many of you are familiar with this. It's called GeoGebra, right? It actually, it is a software that helps you draw graphs. So notice this, you can go closer and closer to 0, and this is exactly what is happening. So what is happening is, and the exact opposite, you might have, maybe you have already seen the other example, right? Like let's call it g of x equal to x sine 1 by x. This maybe you have already seen. Here again, the same thing is happening. The frequency is increasing and the altitude, however, is decreasing. As x is coming closer and closer to 0, the frequency is increasing, but the altitude is becoming smaller and smaller and smaller. That is what is happening when you take x sine 1 by x. The opposite factor is happening when you are taking 1 by x sine 1 by x. The frequency is increasing, the altitude is also increasing. Right? Because 1 by x becomes very big. Sine 1 by x is bounded, 1 by x becomes very big. So that is what is happening when you are doing this. Right? So that's how you should visualize this. And for the same reasoning as why sine 1 by x satisfies the intermediate value property, the other one also, this 1 by x sine 1 by x also satisfies intermediate value property. So that's exactly the kind of thing that I wanted to say, right? So it's again, maybe you should spend, like, in the sense, I don't know, there's a lot to, like, there are some restrictions. We just have 4 hours or whatever. I think the time is short in some sense, but maybe I'm just telling some ideas, and then more exploration can be done on these. Again, I will quickly tell the last point also. So the other points, the example for this is also similar. The other point also, the example is very similar. The idea is, again, it uses sine 1 by x. Okay. Notice that sine square 1 by x. Okay, let me not be lazy. F of x is equal to sine square of 1 by x. Sorry, 1 by x if x is not equal to 0, and 0 if x is equal to 0. G is equal to cos square 1 by x if x is not equal to 0, and 0 if x is equal to 0. Then notice that f and g will both satisfy IVP. Okay, these both satisfy IVP. Of course, there is some work to see that it satisfies IVP, but both these functions satisfy IVP. On the other hand, you can show that f plus g, because sine square plus cos square is equal to 1, what happens is that this becomes 1 if x is not equal to 0, and becomes 0 if x is equal to 0. And that clearly does not satisfy IVP. Because of sine square plus cos square is equal to 1, this satisfies.
So we can use that same function only what you have given, right?
Yeah, this function. That's what I'm trying.
No, the one that you have given before, sine 1 by x with the.
No, but now we are showing something else. We are showing that even see, we would.
No, I understand what is your point. So if I just use sine 1 by x for x positive, and then I use minus sine 1 by x, then same thing will happen. I will get a jump discontinuity which will not satisfy IVP.
No. That does not work. If suppose you take sine 1 by x and minus sine 1 by x, that does not work. Why does it not? Because the sum of it will be 0.
No, sir. But we'll have, let's say, at 0. So at 0, there's a problem. So if I complete that, sine 1 by x, if x not equal to 0, and I will put 1 at x equal to 0.
No, but that here you want to put 1.
1 at x equal to 0.
And g of x is equal to?
Same way, I'll put minus sine 1 by x.
Okay.
And then
Okay.
I'll put 0 at x not equal to 0.
You want to put 0 or 1? 0.
No, I'll put 0.
Okay,
Anything which is like, it will not subtract.
Okay, anything. So if x is equal to 0. Oh, okay, now I see. So f of x plus g of x
will be 0 for x not equal to 0.
Will be 0 if x is not equal to 0 and 1 if
x equal to 0. So we have a jump here.
Awesome, awesome. So this is a correct example. Very good, very good. Thanks. This is also a good example. Very good. In fact, there is no special about 1. It could have been any number C.
Yeah, A and B, if we just take any number, condition it should not be like sum should not be equal to 0. So
great, great. Nice, very nice, very nice. So that is also a good example. So very nice. Anyway, so this is I think it's now time, so I should probably stop here. So most of these ideas actually, many of these ideas I took from this book called A Radical Approach to Real Analysis. Okay, so it's a book by David Bressoud. Okay, that's the book from which I got many of these ideas. Of course, that's not the only book, but that's the idea where I got most of the ideas in this. So I think one of the things you can do is, and that book is amazing in a lot of senses, I would say. Why? Because it gives you these kind of intuitive understanding about many things and how these ideas developed, how it shaped our mathematical thought. All those things are very nicely described in that. So I highly encourage that you have a look at that book. It will be very useful for you. So yeah, I can share you just a minute. Let me just quickly find it. Radical Approach to Real Analysis. Just a minute.
Sir, can we say in general continuity and IVP has no relations? In general.
No, there is a relation.
But there are functions which satisfy IVP, but it is not continuous, like function sine 1 by x not equal to 0. Correct. And there are functions like from Q to R, like x, f of x is equal to x. So it is continuous, but it doesn't satisfy IVP. Correct. So, yeah, so there are, I think we can say that, no, that means in general there is no relation between with some extra condition. Yeah, we have some relations, but in general we have no relation between continuity and IVP.
Okay, that's what there is no relation does not make sense because there is a relation. For instance, continuous function satisfies IVP.
Depending on domain, I think, no? Depending on the domain.
IVP is defined on the connected domains only.
Yeah, continuous functions on an interval satisfies IVP.
Yeah, that is true. But if we take like as a discrete space, like a Q.
No, IVP is defined, I guess, on connected domains only.
No, that's not.
IVP is
that's not true.
Okay.
IVP is a property. Like given 2 points, you can define it for anything. So that's not necessary. So it is defined for any domain, and you are absolutely correct. So only for connected domains, continuous functions on a connected domain satisfies IVP. That's correct.
So am I getting? Am I right or not? That is continuity and IVP are in general, without mentioning the domain or something.
That's what. Like. See, not related is not correct.
That is something harsh, I think.
Yeah, that is harsh and not correct. Yeah. They are not related is incorrect, but they are not one and the same.
Yeah.
That's what I meant. IVP does not imply continuity. Continuity does not imply IVP. That is correct.
It means that it's like a language problem.
Yeah, so that's why there is a relationship. The relationships, as I said, there are so various relationships, but this is correct. Continuity does not imply IVP in general. IVP does not imply continuity.
Continuity in general. Yeah,
that is correct.
Yeah, thank you.
That's the correct statement. So, I've shared the link. I don't know. You find I'm not going to share the the copy of the book. You find it somehow. I've shared the book, what it is. You can have a look at it. So that's it. I think I've already gone beyond time, 10 minutes beyond time. So maybe I should, if you want to ask me anything or say anything, that I would be happy to answer or happy to listen.
Sir, how does IVP make sense over a disconnected domain?
So IVP is this. What is IVP? IVP is a property, right? What is the property?
Yeah, IVP is property, but I mean, we define a property to make some sense over something, right?
Correct.
So yeah, correct. So how does IVP make sense over a disconnected domain?
Exactly. Let me tell that. So what is the definition of IVP? IVP is simple. Given 2 points A and B in the domain, okay? Given points A and B in the domain with A less than B, okay? You look at f of A and f of B. Take any value between f of A and f of B. We say, sorry. Okay. Let me say it properly from the beginning. We say a function satisfies IVP if the following happens. Given any 2 points A and B, such that A and B both belong to the domain with A less than B, then if you take any point C between f of A and f of B, there will exist a point D between A and B such that f of D is equal to C. This is right.
Right.
For this, we don't require the connectedness of the domain.
Yeah, I agree completely. So, but
of the
yeah, I mean, I agree on this completely. On the definition does not require at all the connectivity. I mean, the connectedness. But my question is, I mean, what do we do with the IVP over a disconnected domain? Because what I understand is the main reason, I mean, main motivation behind IVP is to create more connected sets as images of continuous functions. So that is where, I mean, I am a little bit confused that what do we do with IVP over disconnected domain? What are its purpose?
That is a good question. So it's not that there is, see, the thing is, the whole idea of connectedness, right? So that's a very, very good question. Thanks for asking this question. Very, very good question. Very, very insightful. It's clear that you are seeing it. So you are absolutely right that the usefulness of IVP comes when you are working on connected domains. That is correct.
Exactly.
But however, the issue is that this idea of connectedness is not so easy to understand. In fact, when I took something very simple like 0, 1 and 2, 3, there the disconnected, that fact that it's disconnected is so obvious for us.
Right.
In general, whether a set is connected or not is not easy to see. Moreover, this notion of connectedness comes much later than most of these ideas of continuity and stuff like that. In fact, when we are teaching these things, we cannot even use these ideas of connectedness because
of course,
what is the meaning of connected and all those things. So that is the only reason why we cannot really go into those things, because it's a more tricky and involved thing. So historically and pedagogically, we cannot really take resort to those.
Yes, I understood.
That is the only. Your question is very valid. Yes, the usefulness comes when the domain is connected. Otherwise, it's not useful.
Yeah, I mean that is what my point is. I mean, according to my knowledge, that IVP is defined because it is not useful over disconnected domains. It is defined for the connected domains only. That
is not true, however. That is not true.
Okay.
For everything. So. Yes, the usefulness comes when it comes to connectedness, because the whole point is that we don't refer to connectedness when we are studying analysis.
Yeah,
we don't refer to connectedness at all. Actually. So that's the point.
Okay, thank you so much. It was very intriguing lecture, sir. Thank you so much.
Insightful question. So, okay, so I think that's it.
Yeah, thank you so much, Divakaran. I think I don't have to mention it. The enthusiasm and the participation in the session shows that how wonderful it was. Thanks for making all of us think about the definition of continuity again. And also, I think it makes a point that sometimes we take the definition for granted and we don't really question why a definition is what it is, why it is not something else. So thank you for making us, think about all these things. So thank you so much. Yeah.
Thank you for giving me this opportunity.
Thank you, sir.
I may
Very
interrupt
informative.
once, Divakaran. Yeah, so, very nice talk. I wanted to just ask one thing. Maybe you can address it tomorrow when there are more participants.
Yeah, sure.
Is from the MA, right? No, what I wanted to ask was in preparation for this TW, I was looking at this. MA has a whole resource for teachers. I have never used them, so I did not actually suggest that. But maybe if you have looked at it, is it something that is useful for they have a whole resource page for teachers with all sorts of articles and also subject-wise and also some general stuff. You know anything of it?
No, I don't know much about it actually. Okay. There is one thing I know which is very useful, which I have used to some extent. I still want to use it more. There is something called the Triumph series, which I have seen, which I like very much when I am teaching.
Okay.
That gives some historical, like the original textbook, original text, started and reference to that, and of course making it very accessible to current generation also.
Okay. Yeah.
That is something very useful.
Yeah. No, that's why I don't know. I looked at this MA page, so I just wanted to ask you if it's something you know.
I've not looked at it very carefully. So
okay. Thanks.
Okay. Yeah. Thank you so much. Then good night. Then we will meet again tomorrow. Yeah. Bye.